Okay, so allow me to introduce Charalampos Papamanthou, Babis. Most of you probably already know him. He's a director of the Maryland Cybersecurity Center, an associate professor in the electrical and computer in the Department of Electrical and Computer Engineering at Maryland. And he'll be joining Yale University very soon, so he can tell you more about that towards the end of the talk, let's hope. And today he will be presenting distributed authenticated data structures and their applications. So Bobby, the floor is yours.
Thank you very much, Dionysi, and thank you very much for the invitation. So today I'm going to talk about a project that we have been doing recently on distributed authenticated data structures and their applications. So first of all, I'd like to thank my collaborators in advance. I'm working on this project with a very set of smart people. So Alex Cepurnoy from Ergo Platform, who was actually a speaker in the seminar, I think last week. Shravan is my PhD student at Maryland. Alim is at VMware Research, and Yupeng is a professor at Texas A&M. Okay, so the talk outline will be as follows. So first, I'm gonna define what are distributed authenticated data structures. And so let me, okay. I'm gonna define what are distributed authenticated data structures are. Wait, what's going on? Okay, so then I'm gonna propose our authenticated data structure, which is multilinear tree. Then I'm going to talk about applications of distributed authenticated data structures in stateless cryptocurrencies. And then I'm going to conclude the talk with some open problems. Okay, please feel free to unmute yourself and ask questions as I proceed with the talk. Okay, so let's get started. So what are distributed authenticated data structures? So in order to define, I would first like to recall what is the standard authenticated data structures model. So one version of the model is the following. So you have, say, like an untrusted server. It can be a cloud that stores an authenticated data structure. That is the data elements and some sort of authentication information on top of the data elements. You can think about this as a simple Merkle tree, and the data is just like vector entries, like x1 to x8. And of course, this Merkle tree defines a digest, right? So this digest is being stored at the trusted client, so to say, and the cloud that stores the authenticated data structure is untrusted. So there's a couple of things that are going on here. So first of all, the client can issue queries to the authenticated data structure. So for example, can you give me the value of position I? And the authenticated data structure returns, okay, so this is the value xi, and here's a proof. So this scheme here like kind of indicates the path in the Merkle tree, right? And it makes a claim about a value at a specific index. It provides a proof. And what does the client do? The client will take this claim and the proof and will verify the claim using a digest. Now, at the same time, what can happen is the client can say, okay, I want you to update value x3 from x3 to y. So I want to do an update in data structure. Okay, so the server can also make a claim about the update, and it can provide an update proof, which can be used from the client to update the digest. So this is a standard authenticated data structure model. So everything is stored on a specific server, and you can have this interaction. Now, what is the distributed authenticated data structure model? So most of the things remain the same, but there's some major differences. So you still have a client with a digest, right? And now you have this authenticated data structure on a set of elements, the same set of elements. You can consider the elements from before. And what happens now is instead of putting this authenticated data structure on a single server, so what you're going to do is you're going to distribute the authenticated data structure on multiple servers. So here, for example, we have put arbitrarily put the proofs for x1 and x2 in one server, the proofs for x3 and x4 in another server, and so on and so forth. So not all the information lies on a specific server. Okay, so at that point, now if you want to query, for example, for a proof for X3, you can contact the server that stores the proof, and you can get the proof for that, and so on, right? Now, the interesting thing is what happens when you want to do an update. Okay, so this data structure now can go away. So now, what is important for distributed authenticated data structures is to have this notion of state-independent updates. So what is a state-independent update? So say you want to update, so there's an update that's coming to the system, update X3 to Y, right? So in particular, only this information will be provided to the parties that store the data structure in distributed fashion. And now the parties should be responsible for actually updating the proofs that they have, because if you change one element of the data structure, all the proofs will be affected. Okay, so what happens is this update goes to all the parties, and somehow, without nothing else provided to the parties, they have to update their proofs. And also the digest also has to be updated here from black to green. Okay, so this is basically one requirement for distributed authenticated data structures, what we call state-independent updates. So you can update proof for an element, specific element, without having any other proofs, right? So this is important. Okay, now the second very important feature I want for distributed authenticated data structures is to have this notion of aggregation, right? And all of these things are inspired by the application that we're going to end up talking about in the end, which is a stateless cryptocurrency. So what happens with the proof aggregation is that you want to have an aggregator that is going to read, say, a couple of proofs, like a certain number of proofs from for a specific party. And what this aggregator needs to do is to take these proofs, X3 and X4, and produce, like, kind of merge them in a single proof that is going to serve as verification for both X3 and X4. Okay, so this is the second thing that it is important for this notion of distributed authenticated data structures. Okay, so let me talk a little about what do we know so far about this primitive, right? So first of all, let's talk about the very basic authenticated data structures, Merkle tree, and see if this satisfies these properties. So unfortunately, state-independent updates are not possible in Merkle trees. So when you want to update a specific proof for an element, you need to have other proofs for other elements as well, right? So you cannot have state-independent updates, right? So with that, I mean, if an element X changes in a Merkle tree and you want to update the proof of an element Y, you need to have the element X and its proof, right? But remember, in distributed data structures, we only need to have the element X and nothing else. So state-independent updates are not possible in Merkle trees. And of course, proof aggregation is not possible as well naturally. You cannot aggregate this hashes in Merkle trees, right? So now, a few years ago, actually, Catalano and Fiore proposed this vector commitment, which can be viewed as an authenticated data structure, right? Where there you have state-independent updates, right? So if I change an element in the vector commitment, you can update all other proofs in the vector commitment by just reading out this element, right? But the thing is here, you need to spend time that is proportional to the number of proofs you're storing, right? So if you store 1,000 proofs, you need to spend time proportional to 1,000 to update all this 1,000 proofs. And the proof aggregation size is constant. So n over p here, I just assume that you have p elements that, so you have n elements and you have p parties, and every party is storing n over p elements. So that's why I'm saying that the state-independent updates in Catalano and Fiore takes n over p. Okay. So there was some recent work by Tomescu and others in SCN that achieves state-independent updates in n over p and has proof aggregation constant. There's some recent work in point proofs that has the same complexities. And there was some work of mine back in 2013 where you can have state-independent updates in log n time. So it kind of achieves this efficient notion of state-independent updates where you can update every possible proof that you're storing in log n time by using a data structure. And the proof aggregation, however, you cannot do. There was a PhD thesis of Aline in 2019 in MIT, supports state-independent updates, but unfortunately it cannot do aggregation. So it has similar properties with a lattice-based data structure. So the multilinear tree I'm going to talk about today supports both state-independent updates and supports proof aggregation. Okay, so this is the main thing that I'm going to be talking about today. So again, state-independent updates is when I can update proof for element Y by just reading out the update that took place in some other index of the tree and nothing else. Okay. Okay, so let me delve into the specifics of the multilinear tree. So multilinear tree is basically another version of a Merkle tree, but it has some algebraic structure embedded into it. Okay, so let me start by defining a commitment for a vector of 4 elements. Okay, so again, the data structure that we're considering is a vector that has a certain number of elements, and the queries for which we provide proofs are queries of the type, give me the value that corresponds to a specific index. Okay, so we're going to begin with a structured CRS. So if you have 4 elements vector, you're going to need to publish this group elements. So you can view G as elements of some prime order groups that are the source groups of a bilinear map, right? So you have 4 elements, you need 2 variables, S1 and S2, and you publish all the possible combination. If you have like 8 elements, you're going to need 3 variables. Again, you're going to have 8 elements, right? And so on and so forth. But this is just for an example. So this is a structured CRS, okay? Now, how do you compute the commitment for this specific vector? Okay, so first of all, you're going to define this multilinear polynomial, so which is basically a sum of selector polynomials. It's 4 elements, so you need 2 variables. So this is the polynomial 1 minus x1 times 1 minus x2 plus 2, x1 times 1 minus x2, and so on and so forth, right? And the good thing about this polynomial is if you give the binary representation of specific indices, you get back the actual value that is stored in the specific index. So for example, if you give 0, 0, you're going to get 5 because everything else is zeroed out. If you give 0, 1, you're going to get 2 because everything else is zeroed out. Okay. So what is the commitment to the vector? Actually, the commitment is just G to the f of S2, comma S1, right? And then it is easy to see that you can compute this commitment by just using the structured CRS, right? Because you can basically write out this polynomial as a sum of terms that only have S1, S2, and S1, S2. Okay, so this is how you compute the commitment for this vector, 4 elements. Now, so how, okay, so I have this commitment, but a vector commitment serves, it's useful when you can open it, you can convince someone that this value corresponds to a specific index, right? So how you can open a commitment. So this comes back actually from a paper of ours from 2013. So what you can do is you can compute this polynomial decomposition, right? So this is a log n for n elements. This f of x has log n variables. So you can write down this polynomial decomposition. So f of x minus f of t. So t is the binary representation of the index you want to open, and f of t, of course, is the actual value that corresponds to this index. So you can write this as f of x minus f of t equals the sum of xi minus ti times qi of x, right? Right. So if ft is indeed corresponding to the real value that stores at index t on the commitment f, then you should be able to write down this equation, and you should be able to compute these quotient polynomials that we call qi of x, right? So the opening then contains commitments to the polynomials qi, which is g to the qi of s, right? So no, the opening contains the commitments qi, which is g to the qi of s, where qi are the polynomials that are derived by the equation above. Okay. Okay, so I just want to give you an example now. So say you have, this is the multilinear polynomial for the vector 5, 2, 8, 3, and say the prover wants to convince someone that the value at position 0 is 5, right? So what is the prover going to do? So it's going to compute this decomposition, f x1, comma x2 minus 5 equals x1 minus 0 plus q1 x1, x2 plus x2 minus 0. So these two zeros come from the fact that we're interested in the position 0, 0 times q2 x1, comma x2. Okay, so that's how you compute the decomposition. And again, the opening is commitments to the polynomials q1 and q2. And how do you do the verification? Well, if com is the commitment to the polynomial length, you're going to use pairings to, and vi is the position that is claimed to be the one corresponding to the index I. So you're going to do, you're basically going to verify the equations that are presented before using pairings. Okay, and this is not really groundbreaking. This is not really new, because if people, I'm sure in this audience, people have seen KZG commitments. Okay, so this is really a generalization of the KZG commitments for multiple variables. That's what it is. So KZG commitments allows you to open a polynomial on any value, right? A univariate polynomial, right? So we just generalized the scheme back then to open this polynomial to arbitrary values by just generalizing the decomposition that you can do for multiple variables. Okay. So, and here actually we define the polynomial to be a multilinear extension of the vector. So we can cast this multivariate commitment as a vector commitment, because an opening of this polynomial to a specific index actually gives you the value of the vector at this specific index. Okay. Good. So let's see what are the complexities of this vector commitment so far. So the opening is order of n. So there is a way to compute this division so that you can actually get this polynomial commitments in order of n. The verification is order of log n. Again, n here is the size of the vector. So the verification here is order of log n, because there is log n quotient polynomial commitments that you need to read and run the pairing check. The proof size is order of log n, because you basically have this log n quotient commitments to the quoted polynomials, and each commitment is constant size, right? I forgot to say that, right? The quoted polynomial can be big, but its commitment is constant size, right? And the update commitment algorithm is constant. Why? It is very easy to see why you can update this commitment in constant time, because if you want to change a value in this vector, all you need to do is kind of take the delta, right? So get the selector polynomial, remove what is already there, and just add what you want to add, right? So basically, to update the commitment, when you change a value vi to a value wi, what you need to do is to run this equation. Comf equals comf times g to the selector of I times wi minus vi, right? And the g to the selector of I, these are polynomials that are part of the common reference string of the structure reference string has been computed in the beginning. Okay, so far I've presented a vector commitment has these properties, right? Now the question is, how do we take this one step further to actually make the distributed authenticated data structure? Okay, so the central question I'm going to be talking about for the rest for another 10 minutes or so is how we can devise an algorithm that can compute all openings, all proofs in a sense for all indices, right? Okay, so let's see. I mean, this is a question that can be answered easily given what I have talked so far. Well, one naive algorithm is to do like an order of n squared computation. Basically, you have n openings to compute. Each opening takes linear time. So by just doing this naive computation every opening n time, you can do n squared. Okay, but what we want is n log n, and if we do that naturally, this will give rise a data structure that can update all proofs in log n time actually, and this would achieve actually our complexities. Okay, so let me give some definitions first. So imagine you have this vector of 8 elements, v1, v2, v3, v4 through v8. Okay, so let me denote with f the multilinear extension of this vector. So to write down the multilinear extension of this vector, because you have 8 elements, you need 3 variables. And this is how it is. I couldn't fit all the terms here. So you start 1 minus x1, 1 minus x2, 1 minus x3 times v1, and so on and so forth, right? Okay. So now what you want to do is you want to define some other multilinear extensions. So you want to define the multilinear extension of the left of the left part of the vector, and you want to define the multilinear extension of the right part of the vector. Okay. So this is going to be FL. This is the multilinear extension of the first 4 elements. Because it's 4 elements, this multilinear extension will have 2 variables, x1 and x2. And you can write it like this: 1 minus x1 times 1 minus x2 v1, and so on and so forth. And fr is the multilinear extension of the right part, which is again a polynomial with 2 variables, but has different values now: 1 minus x1 times 1 minus x2 v5, and so on and so forth. And now you can continue doing that, right? So you're going to have FLL, a multilinear extension only with 1 variable, FLR, FRL, and FRR. Okay. So far I haven't done anything. I have just defined this multilinear extension of subvectors of this big vector. Okay. So now how we're going to use this? So how we're going to use this multilinear extension now to actually build the multilinear tree, which will enable us to update all possible proofs fast, right? Okay. So this is a multilinear tree. Okay, so the way it works is that we're gonna have as the root of the tree fr minus fl. We're gonna have as its siblings flr minus fll and frr minus frl, and so on and so forth. So you have this way of writing down this multilinear tree. So what does this multilinear tree tells us? So let's look at it, right? So first of all, it stores commitments to these polynomials. So the root of the multilinear tree will store a commitment to the polynomial fr minus fl, and so on and so forth. It doesn't store the actual polynomials, just commitments to these polynomials. And why is it useful? Well, it is useful because if you compute it like this, then you can go down a path and pick up the quotient polynomials for this specific index that you're trying to prove. In particular, here in this design, if you want to prove the value for index 0, 1, 1, which was right for index here it's 3, right? For index 3. So what do you need to do? The first quotient polynomial is fr minus fl. The second quotient polynomial is flr minus fll. And the third quotient polynomial is flrr minus FLRL. That's it. So you need 3 quotient polynomials. You can pick them up from this data structure, right? So now it is interesting though. The amazing thing is that these things are shared, which means that if I want to figure out the quotient polynomials for another index, there will be sharing of commitments on this tree. Okay. Okay. So let me give here an example. So for example, you can write, so if you want to figure out what is the proof for element 0, 0, 0, so you can write the decomposition of polynomial f as follows: f equals x3 times fl minus fr, so this is the quotient polynomial of the root, plus x2 flr minus fll, plus x1 fllr minus fll, plus f0, 0, 0, right? So this is exactly the decomposition as we presented before. Now, if you want to take another index, so this is the index, for example, 0, 0, 1. The first quadrant polynomial will be the same. The second quadrant polynomial is going to be the same, and only the third quadrant polynomial is going to be different, right? So here, I guess, right? So no, actually, even the last quadrant polynomial is going to be different. It's going to be the same. The only thing that changes here is that the multiplication, the decomposition is different because the last bit is 1, right? So you can basically write it like this. Okay. So now, but why? How did I come up with these polynomials? Well, to actually argue that this decomposition that I have written here are correct, the way to prove it is as follows. So you develop the left part, you write out the decomposition, right? And you develop the right part, you write down exactly the multilinear polynomials, and you will see that these are exactly equal. And the main property that we use to prove that is basically that you can write the multilinear extension of f as 1 minus x3 times fl plus x3 times fr. And this is very easy to see that it holds, right? And then you can apply this formula recursively for FL with FLL and FLR, and FR with FRL and FRR. So if you apply this formula recursively, you will see that you eventually come up with these polynomials on this multilinear tree that have the shared quotients that are being used to serve all proofs. Okay, so this is the multilinear tree. So now, what is the complexity of computing this multilinear tree? Okay, so the complexity of computing the multilinear tree, you can write it down very easily. So how long does it take to compute the root? So remember, the FR is a commitment on a vector of n over 2 elements, and FL is a commitment on a vector of n over 2 elements. And since computing a commitment is a linear time operation, so computing the root is just n over 2. Now, FLR is a commitment on a vector of n over 4 elements. FLL is a commitment on a vector of n over 4 elements. So computing this node is n over 4, computing the other node is n over 4, computing all this node is n over 8. So it's easy to see that this is n log n. Okay, so computing the multilinear tree is n log n computation. Okay, now, so this is the most interesting part, right? So how you're able to update the multilinear tree. Now, the interesting thing is that if you think about how Merkle trees work, right? So say an index f0, the value at index 0, 1 will change, right? Now, to update the proof for another arbitrary index in the Merkle tree, you will have to provide the proof for this index that changed. Now, the good thing about multilinear trees is you don't have to do that, right? So for example, say we have FL is 1 minus x1 times 1 minus x2 times v1 times plus x1, x2 times v4. Okay, remember, this is exactly what FL is. Now, if you change an element that affects this commitment, right, from v2 to v2 prime, for example, it is very easy to actually update this proof, right? Because what you need to do is it's the same thing as updating the digest, right? To update the commitment to FL, FL, when VI changes to WI, what you need to do exactly the same thing you did for the vector commitment. You write down the equation FL equals FL times G to the selection of I times WI minus VI, okay? So if I give you a proof for an element and the proof has been computed using this multilinear tree, and another element in the vector commitment changes, I can just take this change and apply it to my existing proof for this opening for this index, and then I can update the proof. And not only that, by applying this change, I'm updating at the same time all possible proofs for all possible elements in the vector, right? Because only the shared elements are affected, right? Sorry, only log n things are affected, and these are shared by many proofs. So this is, you maintain this data structure of proofs. Okay. So basically, I presented this data structure so far that allows you to update proofs for specific indices by just reading out the updates, right? And also it allows you to update all proofs in just log n time, right? Okay, so you don't have to go individually to work on this proof. You just work on this data structure and allows you, which is actually a property that is also shared by Merkle trees, right? Okay, so proof aggregation. Again, remember one of the main limitations of Merkle trees is that you can also not do proof aggregation. You cannot compress multiple proofs. So let me just start now and tell you how we're doing proof aggregation in this multilinear tree. So the way to do proof aggregation is we're actually going to use some existing work about that. So let's talk about a single proof first. Remember that to verify a specific proof for element I, what you need to do is you need to run this pairing equation, where you take the commitment, you take the claimed value vi, and you compute a product of L pairings. Here L equals log n, okay? And remember, Sj minus Ij, the Ij's are the specific bits of the index that we're opening. Now, so this proof, again, contains all the Qj's. So the proof for opening a vector commitment is log n size. So what we're going to do is we're going to use decision work by Benedict Bunz, Mary Mahler, Pratyush Mishra, Tyagi, and Vesely. We're basically saying that if we're going to build a custom proof system for pairing products, and it's exactly what we have here, right? So take the system, you apply, and then you basically go from L, which is the number of proofs that you have, to log L, right? Number of elements to log L. So you can shrink even more the proof size of this pairing verification. The way this proof system works is that you have a public statement. The public statement here is com and g to the minus vi and g to the sj minus ij. And this proof system is an argument of knowledge of qj such that this equation holds. Of course, again, you can have such a proof system, but just applying snarks generically on this equation. The main motivation of this work, the main contribution, is that we're able to build something much more practical and much more efficient than just tailored on this pairing products and just naively applying snarks. Okay, so the first step then is to understand how we can apply their system to just compress a single proof, but we're not done yet. So this is not, we're just saying how to compress single proof. Remember, proof aggregation requires to take a bunch of proofs and compress them in one proof, right? So how we can take this to one step further? So you're going to have to compress m proofs here, right? So say you have a proof for vi, which is verified using this pairing equation, and a proof for vk, which is verified using this pairing equation, right? So what you're going to do is the prover will first commit to the polynomial to the polynomials qjk and qji, and then we're going to pick random ri and rj to verify the following combined linear combination of the above equations, right? So this is standard technique where you want to verify two separate equations. You're going to take the random linear combination. It's important for the prover that commits first to the qik and the qjk, and then you take this random linear combination. And in this way now, we managed to cast multiple verifications into a single verification, and then we can use we can actually use now the paper by Bunz and others, and we can go from the initial proof size, if you had m proofs, is m times L. Now, by applying this work to the random linear verification, you go to log m times L. Okay. Okay, so this is how proof aggregation works, and so let me actually now talk a little bit about the application of the stable authenticated abstractions to stateless cryptocurrencies. So storage and computation in cryptocurrencies has becoming an issue. So here is the size of the Bitcoin blockchain from 2010 to 2018. Now, the problem is that it's not only the ledger that grows, but also the actual state that you keep to verify transaction also grows. Like this can be like the UTXO in Bitcoin or the actual account balances, right? So this creates a problem in a sense when you want to start verifying transactions right away, you have to download this huge vector of balances in Ethereum, or you have, which comes with this Merkle tree, or in a Bitcoin, which is not that important, you have to download this UTXO. The UTXO is, I think, is a bit smaller, right? Now, it's not only downloading and syncing the problem. Once you have this account balances and the UTXO, if this is big, you might have problems with accessing because you have to store it in disk, and there was some kind of attacks that were reported where there was some DOS, right? Because of that, so storing like this big state can lead to this DOS. But also recently, there is a lot of interest in this stateless validation by the Ethereum community, where they're considering this notion of sharding, where when you change shards, you have to kind of get the validation state that you're using from one shard to another shard, right? And it will be nice if you don't have to actually send out balances like this huge vector of balance all the time, but you just exchange like a small digest of balances, right? So this is something behind the motivation of why we want stateless transaction validation in cryptocurrencies. So there's been a lot of work starting on this stateless validation and what are the challenges to achieve that. So the first work that appeared was actually by Leonid Razin, Meskov, Chepunov, and Ivanov in 2017. That was actually an invited talk in the Real World Crypto conference, when they first talked about using Merkle trees to kind of get rid of the state for miners, so that you just verify using just Merkle tree proofs. So that was the first step. Then we had the first version of Hydrax, and then we have various other works where they use cryptographic accumulators to compress the state. Have aggregatable subvector commitment for stable cryptocurrency, and recently we also had this work on point proofs, where the main actually motivation was to get rid of the state. Okay, so before I describe how our multilinear tree can be used for stateless validation, let me try to talk a little bit about stateful transaction validation and how it is being done right now, say in Ethereum. So what happens now, you have a miner that stores this balances. So here you have public key A has 8, public key B has 5, and so on and so forth, right? And now, when you want to actually send money, so from A to E, say 7 Ethereum, so what happens is you send this transaction, and the miner, the first thing he's going to do is he's going to check that there is enough money at A's balance to actually support this transaction, right? And once this is established, what he's going to do is he's going to update the balances from A is going to be 1 and E is going to be 12. Okay. So this is how it works now. So for this to work, you need to have access to this huge vector of balances, right? So what we're suggesting and what the stateful validation is about is, okay, you don't have to store all the vector. What you need to do is just store this digest of this vector, right? So you can view this as a multilinear tree now, right? Okay, so you're gonna store all this digest, or you can view it as a Merkle tree for this example, right? And the miner just stores this R. So now how does it work, right? Since you store only R, if you make a claim about sending money from B to G and you don't do anything else, then there's no way for the miner to check that B has enough funds to support that. So what you need to do is send actually a proof, right? And this is a proof how to do in a Merkle tree, where basically says, okay, I want to send money to G, and here's a proof of my balance. And since I can prove to you that I have more money that I want to send, you're okay, you're good to go, right? So you can send this proof here, and the miner with Merkle trees can verify that indeed this transaction is supported. But the main problem is, if you use Merkle trees, you cannot go ahead and update the balance of G. Because for you to do this, you'll also need the proof of balance of G. But that means that somehow I need to connect to G and ask him for his proof, right? But this goes completely against the notion of cryptocurrencies, where, you know, people do not have to be online or like talk to me in order to receive money, right? So what I want to do is I want to say, I want to send money to this public key, and you know, this is, and when this public key will wake up, the money is going to be there, right? Okay, so basically the main problem with just using simple Merkle trees to support stateless transaction validation is that you cannot really you cannot have a miner updating balances of recipients without actually having the proofs of the recipients. Okay, and this is something that the multilinear tree doesn't have to worry about, because the multilinear tree has state-independent updates, right? You can update the digest or anything by just knowing how much you want to increase the specific value, right? Okay, so that's the main motivation of defining this distributed authenticated data structures. Okay, so let me just now describe how we're going to use this. What is our architecture of IDRAX, which is actually stateless validation using multilinear trees. So here, for example, is the commitment. So IDRAX is a framework for doing transaction validation for account-based cryptocurrencies, right? And in IDRAX, you don't have to store the account of the vector of balances, but what you need to store, which also goes on the blockchain, it's part of its block, it's a digest of this account balances, right? So now say you have Bob, right, that wants to send some money to Alice, right? Now, Bob has, say, Bob controls some certain number of accounts, right? So he has multilinear tree proofs for every single account, which is, an account can be like a position in the vector. So when I say here local proofs, these are actually multilinear proofs for all the accounts that he controls, right? So when he wants to send money to Alice, you know, previously we'll just send the transaction, and because the vector of balance will be stored, you don't have to send any proof. Now it's gonna attach a proof along with every transaction to support his balance, right? So all these proofs are being sent to the miner. So now miner will take this transaction and proofs. It's gonna verify that there is enough balance to support these transactions, right? And now what he's going to do is he's going to update the commitment from T to commitment T+1. Updating commitment means decreasing Bob's balance and increasing the recipient's balance. Again, he can easily do that, the miner, because, you know, we're using a data structure that has state-independent updates. So there's no need to have any proofs from the recipient whatsoever. Okay. So once the miner does that, then it can create the new block, because you have new transactions, right? You update the commitment, so you publish everything as the new block. Now, why transaction aggregation, proof aggregation is very important? Because if you don't have proof aggregation, what you need to do is you need to attach to every transaction in the new block a separate proof, right? Which increases significantly the size of the block. But here we have an aggregate proof that has formal transactions, which means that everybody that downloads this block can easily verify, right? Now, the interesting thing now is that whenever these transactions are executed and the balances change, right, all the proofs from all other parties are also changing, right? And then again, what you need to do now is you have Alice, which has her own local proofs. It needs to read the transaction and actually update her proofs. Okay, so it reads the transactions and update the proofs. Okay, so again, you don't need to have any proofs about the recipient here, right? All of these updates of local proofs and digests can just take place by just reading out the actual data of the update. Okay, so and again here it's important to notice that Alice can update its local proofs in logarithmic time. No matter how many accounts does she control, it just needs to maintain a local data structure that will help her update the local proofs. Right now, one criticism that we have been receiving about this work was this notion of offline clients and the burden that offline clients will have to endure once they come back online. Why is that? So say Alice has her local proofs, right? So, and she's offline for a very long time. Okay, so transactions come in, and the digests are updated. There's all the transactions, and now she wakes up. Normally in Bitcoin or in Ethereum, doesn't have to do anything, right? He wakes up, he can just start transacting right away, right? Because there's going to be a new balance for her, right? But now here, for her to transact, she's going to have to sync her local proofs, right? Okay, so basically this is one problem, right? So this is basically requires for her to replay all the possible updates. Every update will cost log n, but if you have like a million updates that have been a million transactions, then you're going to have to spend 1 million times log n, right? So this is not good, right? So we came up with this other addition to the architecture, which we call this proof serving nodes. So the notion of a proof serving node is to serve proofs to Alice. So when Alice wakes up, it doesn't have to actually download any proof, right, and update her local proofs. You can ask the proof serving nodes to update the proofs for her, to keep updating the proofs, and just retrieves the local proofs from a proof serving node, right? So this is something that the proof serving nodes are untrusted. They're not part of the architecture of blockchain, just untrusted nodes that can serve proofs. And actually, when Alice receives a proof, it can verify easily now, because it has the updated commitment from the blockchain, that the proofs that is being served are actually the right proofs for her. So she doesn't have to compute them from scratch, right? And of course, in the real world, you can have like a kind of like a hybrid of a little bit of proof serving nodes, a little bit of some proofs can be maintained by Alice, right? But this is like an architecture we're currently considering. Now, one thing about proof serving nodes, though, is a very natural question is, why would they ever want to be part of this blockchain, right? Why would they ever want to participate? So we have to give proof serving nodes incentives, right? So to give proof serving nodes incentives, we introduced this notion of unstealable proofs. So what is an unstealable proof? The idea is that I want to be paid for actually providing a proof to Alice, right? So how we do that? So every proof serving node has SK and PK. Okay, so a secret key and a public key. Okay, one could say, okay, so why don't you have the proof serving nodes, once it provides a proof to Alice, right? Why don't you have the proof serving node just sign this proof, right? Well, the problem with that is, if a proof serving node signs the proof with the secret key, right? Then, and it publishes this proof, and some other proof serving node that didn't do any work can just grab this proof and then just compute the signature. So without doing linear amount of work, just grabbing, stealing a proof and just signing it, it will give the same reward, right? So what we did is we want to be able to verify that the proof comes from a specific proof serving node, but we also want to make sure that if someone else is able to resign a proof P from a certain proof serving node, then this means that a certain crypto assumption is broken. Okay, so the idea is, how do we enable a proof serving node to tag the proof, tag a proof, right, with his secret key? And if this tagged proof is given to some other proof serving node, right, there is no way to retag this previously computed proof with another secret key, unless you break a cryptographic assumption. Of course, another proof serving node could, in principle, compute this proof and retag it, but this will amount to a linear amount of work, right? So then you will not have, right, so then it will deserve the reward, right? So it turns out that we can compute these unstealable proofs. We can actually have a cryptographic transaction using multilinear trees. So in a sense, we prove that the multilinear trees proofs are actually can be made unstealable. Okay, and how the main idea is as follows. So the secret public key of a proof serving node is a G to the A, right? And then remember that the opening of a commitment as a specific index, the proof consists of commitments to polynomials. So it's G to the Q1, G to the QL. So instead of computing this as proof, when you are a proof serving node, what you're going to do is you're going to compute G to the AQ1, G to the AQL, right? So it is very easy to verify that this proof comes from a specific proof serving node with public key G to the alpha, right? By using pairings. And of course, this also can be verified by the miners, and they can actually, when they verify this proof, they can actually use this to assign the necessary reward, right? And it's also difficult to retag this proof, right? You can compute it from scratch, but just reading these elements and getting A out and putting something else, it's not easy because you don't know actually A, you just know G to the A. Okay, so we have a proof security for that. So some micro benchmarks. So this is in the horizontal axis. I have 2 to the L, which is the log of the size of the vector, right? So from this table, as you can see, the most costly operation is commitment, which, you know, in principle you only do it once and then you just keep updating it. So open all is also you only do it once and then you keep updating. So update commitment is extremely fast. It's only 56 milliseconds. Update all proofs, it's just, you know, in log and time, it's extremely fast. Verification is fast. Individual proof size is around 1.44 kilobytes. So aggregate and verifying of aggregate are a little bit expensive. So we're working now on actually doing the verifiable aggregation a bit faster, because now it's linear, but I believe there is a way to actually make it faster. Okay, so this, and the aggregate proof size for 1,000 transactions around 52 kilobytes. So these are some macro benchmarks. Okay, so some open problems in this area. So first of all, one main limitation is that we have trusted setup in the distributed authenticated data structure. So we don't know how to do distributed data structures with trusted setup. There might be a way to do vector commitments, but you know, there are a lot of properties that went on top, like aggregation and this state independent updates, which have no idea how to do. So I talked about mainly about stateless validations in cryptocurrencies, but the question is how you can also do stateless smart contracts. One of the limitations there is that if you do stateless smart contracts and you post a transaction, you can compute proofs. You can add proofs for the state of the contract that you own, but when you post a transaction or a contract, you don't know which contract is going to access next, right? So at that point, how do you provide the proofs for the memory locations that are being accessed when the contract you fire goes to different smart contracts? Also, we used for the multilinear tree that we proposed, we used an existing system, which is actually we implemented it, and it's fast. But potentially, if you don't use, if you do something more custom on the data structure itself for aggregation, maybe you will be able to even do much more efficient aggregation. This is something that we've been working on. And also, we don't know this distributed data structures are based on this bilinear Diffie-Hellman assumptions, and we're using bilinear groups. We don't know how to do distributed data structures based on RSA assumptions. So this also potentially might be more interesting, right? Because in our RSA setting, even in the trusted setup, you can have the public parameters are small, right? It's only the modulus, and right, and there's also this new exciting work on class groups. So potentially, if you have something on RSA assumptions, maybe you can have something that it has not set up by using class groups. Okay, so yeah, so with this, I would like to thank you and I'll answer any questions that you might have.
Thank you very much for the talk, Bobby. So let me start with one quick question, which has to do with incentivizing the proof serving. One question that I have here is whether we can write this incentivization in the form of a smart contract. I guess maybe you can do that, but then one problem is that this client that doesn't want to maintain all the state will also need to synchronize to see if it got well to pay into that smart contract or to check if that smart contract is correctly formed. Can you comment on that? Like, is that possible? Is that not possible?
So for the smart contract, I'm not sure how it would help because you will still have to somehow make sure that the proof that is coming from proof serving nodes actually was computed by this specific proof serving node, right? So I'm not sure how exactly the smart contract would help. Did you have anything more specific in mind?
So maybe like if I am a proof serving node and my public key is available, maybe I could create my own smart contract in which I can be sure that I will be paid if I provide the correct proof. So that this incentive can be kind of
right.
I can be ensured. Yeah.
Right. But the thing is, what happens if you provide the correct proof, but someone else steals your proof and also has a smart contract that pays this other person, right? So for example, you make a smart contract, which is exactly what you said, that it can pay you if you provide the correct proof. But when you're providing this proof, right? When you're providing this proof, someone else, before the proof goes to the smart contract, because this is public information, someone else grabs it and sends this proof to his own smart contract, right? Is it clear?
Can you maybe use the unstealable construction that you mentioned in the smart contract itself, or will that not work?
Right. So if this proof is tagged in the way I mentioned, right? So then the smart contract, if someone else gets it, it will not be able to actually replicate this proof, right? But the smart contract is basically going to do the verification, and it's going to check that, if this proof verifies and is tagged with this public key, then do pay this other person, this specific person that has this specific public key, right? But I'm not sure how the smart contract can facilitate the payment and the verification. You can bundle them together, but I'm not sure how it's going to serve the unstealability property, right? Because the unstealability it's still an issue, I think, right? I don't see how it could help, but maybe there is a way. I mean, I'm not sure, but the main problem I see is that when before a proof goes to smart contract, this is public information, so it can be stolen. So you need to have unstealability there before you even go to the smart contract.
Okay, thank you very much. Any other questions from the audience?
Well, if no one has a question, I have a question to the last. To the second part. Hi. So if I got you right, maybe I missed something, but I think you said that the problem of the naive Merkle tree construction would be that we would need the proof from the recipient to be able to update, right? Or the kind of the pod in the tree. But then in the proposed construction, you have these proof serving nodes as an assumption. So I was wondering whether this assumption would actually salvage the Merkle tree construction as well, right?
Excellent question. Yes, thank you very much for this question. Right. So indeed, with the proof serving nodes, you actually can grab the recipient proof, right? So this notion of state invariance is not an issue, but Merkle trees will not work there because we don't know how to make unstealable proofs with Merkle trees. and plus
okay.
we don't know how to make aggregation. So right.
Yeah, of course, that's
and the other thing is also we don't want to be based on proof serving nodes for correctness and for availability, right? Because proof serving nodes are untrusted entities that can go down anytime. So if you want to transact, you want to have this fallback guarantee of being able to update your proofs still if a proof serving node is there. If a proof serving node is there,
yes.
sure. Right? So in a sense, like in an ideal scenario, right, when you don't care about aggregation and you don't care about unstealability and proof serving nodes are always online, Merkle trees will be great, right? But there's this other dimensions in the problem. But this is a very good question. Thank you very much. That's a great question.
Thanks. I see now.
Okay, any other questions? Okay, if there's no more questions, let's wrap it up here and thank Babis one more time. So thank you for your time, Babi, today. And with that, I'd like to invite everyone to attend again next week. We will, as usual, send out an email notification, and our schedule is available on our website. So have a great evening, everyone, and thank you for
very much, Dionisio. Thank you. Bye-bye.
Thank you, everyone. Bye.